Okay, so let's take a look at some examples for normal probabilities and normally distributed variables. All right, so starting with number 1 here, we got the weights of a species of fish in a controlled population are normally distributed with a mean of 5.2 pounds and standard deviation 0.7 pounds. Find for part A the probability that a fish from this population weighs at least 6.5 pounds. All right, first thing we want to do for one of these problems is sketch ourselves a picture. All right, so I got a normal curve. Our mean is 5.2, so I'm going to label the center 5.2. Now we're looking for the probability that it's at least 6.5 pounds. So 6.5 is going to be out here to the right of 5.2, and at least is going to mean we want it to be 6.5 or larger. And since normally distributed variables are continuous, whether or not it's exactly 6.5 is irrelevant. Weights or any continuous variable can't be an exact value, so we always have to have an interval of interest. So it's always going to be an area to the left of a value or to the right of a value or in between two values. Now the next step after we set up our picture is we need to find this area using our table, and we only have a table for the standard normal distribution. So we got to do z-scores before we can go to the table. So we're going to take our data value of interest, 6.5, subtract the mean, and divide it by the standard deviation. If we punch this up on the calculator, throw parentheses around the numerator if you want to do it in one step. All right, so I'm getting 1.86, and we can always round off our z-scores to 2 decimal digits because that's all our table has. All right, so we got to find the area to the right of a z-score of 1.86. All right, so we have this standard normal table. It's available on Blackboard, and we got to pay attention to the fact that this gives us the area to the left of a z-score. All right, so I got to find z-score of 1.86. So what I'm going to do is find 1.8 in this first column. Now I got to find the hundredths place of 6 by basically looking at the hundredths place, scroll across the top of this. So over to a hundredth of the 0.06, we're looking over here. Basically the way this works is now that I find my 1.8, this first number is the area to the left of 1.80 right there. Here's the left of 1.81, 1.82, 83, 84, 85. Right here is the area to the left of a z-score of 1.86, so 0.9686. So it's pretty common for people to think they're done. They've looked up a z-score in the table, but remember, that gives us the area to the left of our z-score. So we essentially just found the area to the left of 6.5 on this normal curve. I need the area to the right. Well, to the left and to the right, this is complements again. The total area under the curve is 1. So to find an area to the right of a z-score that you look up, simply subtract the table area from 1. So we're going to get 0.0314. So pretty small probability, only about a 3% chance that one of these fish weighs at least 6.5 pounds. So we keep the scenario the same here, but now we're trying to find the percentage of fish that weigh between 5 pounds and 6 pounds. So whether it's asking us a probability question or find the percent question, it's really the same setup. We are going to sketch our normal curve, label our mean, and then label the interval of interest. So I'm looking at between 5 and 6 pounds. So 5 up to 6. each different type of area, whether it's between two values or left or right, requires us to use the table in a little bit different way. Since now I have two separate data values of interest, what I'm going to need to do is get two separate z-scores. So in my first z-score calculation here, I'm going to do the 5 minus the 5.2, divide that by my 0.7. All right, that gives me, if I punch this up, that gives me a z-score of negative 0.29. And if we convert the 6 into a z-score, I get 1.14. So now we're trying to find the area between a z-score of negative 0.29 and 1.14. Whatever that area is, it'll be the same as the area in our case between 5 and 6. Here's how we're going to do it for an area in between two z-scores. Take the data value that's farthest right and get the area from the table. So let's see. Let's get rid of the stuff we had last time. All right, so I'm trying to look up a z-score of 1.14. All right, so 1.1 right here, 1.10, 1.11, 1.12, 1.13, so 1.14.8729. Then we're going to take the z-score on the left, and we're also going to look up that area from the table. I'm getting 0.3859, and believe it or not, it's easier to misread a number on that table than you think. Those numbers are pretty small, very easy to let your eyes jump from one row or column to the next. Now, the idea is, when I looked up the 1.14 and got 0.8729, that was the area entirely to the left of 6, or of 1.14 as a z-score. But that's too much. That's bigger than my area. I don't want this part over here that was to the left of the lower value. So what we do is subtract the 2 to subtract away that extra area. So here, 0.784. Here it looks like we have an area of 0.4870. So if it wanted a percentage, I guess we could say 48.7% of the fish in this population would be between 5 and 6 pounds. The more problems like this you do, the quicker you are using the table. All right, let's take a look at another problem. Okay, so entrance exam scores, we've got a mean of 575, standard deviation 65. So part A, what is the probability that a randomly selected student scores less than 450? I'm just drawing my picture. 575 was the mean. We want to find the probability that they score less than 450. Less than is going to be an area to the left. Now, area to the left is exactly what the table gives me. So once I look up my z-score, I'm just going to take the table area and I'm done. Here we'd have 450 minus 575 divided by the standard deviation, which is 65. And punch that up on the calculator again. You'd throw parentheses around the numerator. I'm getting negative 1.92. All right, if we look up negative 1.92 as a z-score in the table, There's negative 1.9, 1.90, 1.91. There's negative 1.92. That gives me the area to the left, which is exactly what I was looking for, 0.0274. So the probability that they score less than 450 is only 0.0274. It's a low probability, meaning not many students score less than 450. All right, let's look at the high side. Let's look at some high scores here. Suppose the college offers an honors program to students who score in the top 5%. Notice they're giving us a percentage now. They're not giving us a test score or a data value. So they're essentially giving an area. This is actually where this is more applied. Usually people aren't terribly interested in taking a specific value from a normal distribution and finding an area under the curve or a probability. Usually they're looking at a certain percentage or certain percentile and figuring out what data value would fit there. So here, what we're going to do, I still like to start with a picture. It's a pretty sloppy and lopsided number line there. But what I'm going to do is essentially work backwards. Let's start with a z distribution, the standard normal distribution, and let's look for a top 5%. Top 5% means this area in the top tail, or the right tail, I want it to be 0.0500. What I'm going to do is try to find the z-score that gives that. The notation the book uses, by the way, is this would be z.05 if it's supposed to represent the z-score, so that the area to the right is 0.05. Whatever that little decimal subscript is, that would represent the area to the right of it. Well, different people find this in different ways. The way I like to do it is say, if I know the area over on the right side is 0.05, then that means the area to the left of this z-score is 0.9500. So what I'm going to do is I'm going to go back to the table and use it in a different way. I'm going to now try to find the z-score that has an area closest to 0.9500 in this table. This one's actually a problematic value to use, which is why I picked it, because if we look at the inside of this table where they give us the areas, we usually just go with the area that's closest to what we're looking for. Problem here is if I'm looking for an area to the left of 0.9500, these two areas are the same distance away. And they come from a z-score of 1.6, scroll up to the top, so they come from the two z-scores of 1.64 and 1.65. So honestly, if it was a test, I'd probably give you full credit for using either one of those two z-scores, because typically we just go with the z-score that is based on the area that's closest. What our book's going to do, since it's perfectly in the middle here, our book's going to say, let's take the average of those two z-scores and let's use 1.645, the average of the two of them. All the hard work is done. We figured out the z-score. The problem is this didn't ask what z-score is needed. It asked what score on this entrance exam test is needed. So there's a couple ways to do this. One way is to interpret the z-score, but the other one is to use this formula that now more people are preferring to just memorize the formula. The formula says that the x value is going to be the mean plus the z-score times the standard deviation. So if you want to kind of just memorize that formula or have it written down, that's how you can easily convert from a z-score to an x or data value. So our data value here is going to be the mean, which in this case was 575. Let me double check real quick. Yep, 575 plus the z-score 1.645 times the standard deviation, which was 65. All right, so if we punch that up on the calculator, I'm getting 681.925 out of it. That doesn't mean we need that number right exactly. It just means the score needs to be at least 681.925. Now they'd probably just say, hey, that's close to 682, so practically speaking, they would probably just round it off. But this would be the cutoff. We would need a score of that value or higher to be in the top 5%. Most students have a much harder time with this type of problem than part A or problems from the previous example. So just kind of maybe go back and try this problem again, just to kind of guard against making the typical mistakes. All right, we're going to continue with this problem here. What if the college wanted to mark students who are in the bottom 10% to be contacted by the college retention specialist? What would be the cutoff? So again, same type of problem. They're giving us an area. They're giving us a percentage. All right, we want that left area to be 0.1 or 0.1000. All right, so let's find the z-score. Again, I'm going to be looking at the middle of this table at these 4 decimal digit values because I want to find the area to the left closest to 0.1000. Like I said, typically we're just going to go with the closest one. So notice we've got 2 that are pretty close, here and here. 0.1003 or 0.0985. Well, the 0.1003 is a little bit closer. Negative 1.28. So that's how I would get my z-score, negative 1.28. All right, so let's go back to the problem here. Z equals negative 1.28. But again, we don't want to say, oh, anything with a z-score of negative 1.28 or less. We want to convert that into a data value. So the data value or the x value is going to be the mean plus the z-score times the standard deviation. The mean was 575. Adding a negative just means subtracting, so minus 1.28 times a standard deviation of 65. All right, so again, if we punch this up on the calculator here, check me out, I'm getting 491.8. So the cutoff would be 491.8. And if they were going to send a notice or get in touch with students in the bottom 10%, you would just need this score or anything lower than that. Okay, last part here. Determine the score that represents the 80th percentile. Well, that's pretty much the same thing, really. It's just in this case. Too bad that didn't say 50th, because the 50th percentile would be the z-score is 0. It would be exactly the mean, right? Because a normal distribution is perfectly symmetric. The mean and median would be the same thing. So the 50th percentile, the median, I could just say, oh, it's 575. Well, it wanted the 80th percentile. So the 80th percentile is going to be a value so that the area to the left is 0.8 or 80%. So again, let's find in our table the area closest to 0.8000. And in this case, it looks like we have two that are close right here, 0.7995 or 0.8023. 0.7995 is closer, so it's going to be 0.8, and then scroll up to the top, it gives us a 4, so 0.84. Alright, that means the x value is going to be the mean plus the z-score times the standard deviation. 0.84 times 65. So I'm getting 629.6 if we punch that up on the calculator. Right, these normal distribution probability questions, people tend to do very well with them eventually, but it definitely takes practice. Do not just watch the video or follow somebody else's work. Make sure you're working through these homework problems on your own. Let me know if you get stuck on any. Good luck, guys. Have a good one.